Hello, everyone. My name is Fabiano Correia from the Master Degree Department of Federal Institute of Espírito Santo, Brazil, and with a partnership with the supervisor Daniel Cavalieri, I will present the paper Thermal Inspection in Equipments of Substation Power Plants using YOLOV8 on the 6th IEEE Symposium on Computers and Informatics. This study has the object to produce an image detection method using the machine learning tool YOLOV8 that allows, without the human visual analysis, the detection and classification of thermal function anomalies on equipment of an electro substation called hotspots. An electro power grid has three main parts: the generation, the transmission, and the distribution. It aims to bring electrical energy in distinct level of voltage to grant the attendance of any type of customers, like other electrical companies, industries, and residents. As shown on the figure, step up and step down substations always appears between the parts of an electrical power grid. Those electrical substations have the keyhole of connect distinct level of voltage across any power grid. They also be part of industrial plants that need to receive a higher level of voltage from the power grid and make proper distribution of the power on their plant. It's easy to realize the importance and the high amount of this kind of plant. The tool YOLOV8 is a set of pre-trained convolutional network models. Those models use machine learning to extract features from images. It has five types of pre-trained models, each one with better precision results, but also a higher computational cost. The feature of the application determines the model used. Following the literature and previous studies, this project will use the lighter model YOLO V8 Nano. The motivation of this paper is to improve the quality of the thermal infrared inspection. Those inspections are part of the predictive maintenance plan of any substation, and it aims to detect hotspots on equipment installed on its yards. The government regulates the periodicity and defines the standards of this procedure. In Brazil, all the equipment on a power grid substation need to be inspected once in a period of 6 months, following the standard for infrared inspection of electrode system rotating equipment published by the Infra-Inspection Institute. This standard introduced this delta T table, defining the priority and action for each temperature level of a hotspot. This paper aims to detect and classify the priorities 3, 2, and 1 because those requires measures from the operational and maintenance team. With this, the project would avoid human errors and time of exposure to electro risk areas and also reduce costs of maintenance. This is the methodology flow diagram, starting with data collected, then hardware description, the pre-process of the images collected, the test configuration of the models, and the metrics that will be used to evaluate the results. About the data collected and pre-process, over 300 images were collected with the operational team of a real substation on Espírito Santo state of Brazil. Those images were produced with the FLIR T650SC camera. As we can see on the left image, the operator makes a configuration to highlight the top temperature of the image by changing the temperature scale and put a set of label information. All those features would certainly cause an overfitting on the machine learning model. To avoid that, the first step was to use a manufacturer application to put all those images in the same scale of temperature. Then use the online feature Overflow to make the identification of those hotspots, the documentation of the dataset, and the crop of the labels on top, down, and right side of the original images, resulting in treated images like the right one. Training and metrics. Once a pre-processed dataset version is done, it will be running through the layer YOLOV8 premodel. The dataset, all of them, will be divided in 70% to training, 50% to validation, and 50% to test. The metric used to evaluate the results will be the precision, since this was the metric used in the articles that made the state of the art of this study. Results. The results were organized on the test control table. Each preprocess used generate a dataset, identified on the column DS. Some main features of the dataset is showed on the table. Then a configuration of the training model is set to produce a precision result. This procedure, this procedure was repeated 9 times. Always consider the previous results to generate a new preprocess and model configuration set. As shown on the table, the test number 8 had the best results with an 88.1% precision on the validation. As the methodology demands, the same configuration of this best result was used on the previous version YOLOV5, showing an evolution of 70.62% on the precision using the YOLOV8 tool. Following the methodology, we run this Bayesian model to predict hotspots on images that wasn't used on the training, the 50% image test. It is important to point that the model didn't have contact with those images so far, working like a real field test. Here you can see some of those predictors. The machine learning could predict the hotspot even in some trick but usual situations, like when happens two distinct levels of hotspots on the same image, or hotspots on higher distance, small size, and several shape and types of electro substation equipment. The figure shows on the first image a hotspot priority 2 in a distant energy line insulator. On the second image, two hotspots priority 2 and one hotspot priority 3 in a bus bar connection. On the third image, a hotspot priority 2 inside a hotspot priority 3 in a bus bar connection. On the fourth image, a distant hotspot priority 3 in a transformer connection. On the fifth image, a hotspot priority 3 in an insulator's connection. And on the sixth image, a hotspot priority 1 inside a hotspot priority 3 in a circuit breaks connection. Conclusion and discussions. The main obstacle of this project was the restricted dataset, ones that the electro companies do not easily allow the access to a large number of images of their yards. The gains are mitigate maintenance costs, reduce human exposure to electro risk area, minimize human errors. Those gains could allow the companies to do some maintenance improvements, like increase the range and the periodicity of the thermal infrared inspection because of the cost reduction. This change would bring operational stability and reliability. Indirect cost reduction with corrective maintenance. Those corrective maintenance are the worst scenario to any electrical company. As an extension of this work, we would suggest an addition of a drone with a thermal infrared camera. This could expand the application to electron transmission lines and any other infrared inspection that have the distance as an impediment. Here we have the reference of this paper. And once again, thanks to IEEE for this opportunity, and thanks to everyone that watched this paper presentation.